Okay, okay. Today's lesson is on average and instantaneous rates of change. So our learning goals are that we're learning the difference between what the average rate of change and the instantaneous rates of change are and how it relates to calculus. And we're learning to apply average and instantaneous rates of change to word problems. So it actually really relates to what we did on the very first day when we were talking about the difference between the slope of a secant and the slope of a tangent. The average rate of change, so average rate of change of a function over the interval x equals a to x equals b can be found using the formula average rate of change equals f at b minus f at a over b minus a. So really this is just finding the slope of the secant. Okay, so you can think of f at b being like y2 minus f at a being y1 over b, if that was x2, minus a, which was x1, because we're going from the interval x equals a to x equals b. So that's why I've got in the box here. This is the slope of the secant joining the points p, a, f at a, and q, b, f at b. And then we've also got a picture. We've also got a picture showing a secant here joining points P and Q. Okay, so average rate of change, you're thinking slope of secant. And then we're moving on to instantaneous rate of change, where now we're thinking slope of tangent. Okay, so you can see it's just the slope of the tangent at a specific point, P, A, F at A. And so then the formula for instantaneous rate of change, use a different color highlighter here, would be now we've got the limit, calculus is involved. The limit as h approaches 0 of f at a plus h minus f at a over h, which you should recognize as that first principles formula from yesterday. So we're applying that, finding the slope of a tangent, but instead we're thinking of finding the instantaneous rate of change of something. So what its rate of change is at a specific point in time. Okay, so instantaneous rate of change, slope of tangent, average rate of change between two different times, slope of secant. Okay, so those are our two formulas. Just some notation. Rather than writing out average rate of change every time, you can write out M for average rate, so M can stand for rate, or sometimes people write V average. Okay, those are both acceptable. And then for instantaneous rate of change, you might want this, so M's standing for kind of like our slope, but for our rate. So M instantaneous, so the instantaneous rate of change, or V instantaneous is also okay. V kind of stands for speed, which is also a rate of change. So both of those notations could be used. Okay, so we're going to move on to a question here where we're going to apply this. So a pebble is dropped from a cliff that's 80 meters high. After t seconds, the pebble is s meters above the ground, where s at t, so instead of f at x, they're giving you s at t, so function notation still, is equal to 80 plus 30t minus 5t squared. And then they're just giving you the restriction that this formula is only valid for times between 0 and 8 seconds. So the first question wants us to calculate the average velocity of the pebble between 1 second and 3 seconds. Okay, so to find the average velocity, then we could do a formula, and it's velocity, so we might as well use V average. So that's going to be s at 3, so our position at time 3 seconds, minus our position at time is 1 second, over 3 seconds minus 1 second. Okay, so then we actually have to find out, so we'll do our little squiggly line here, what is s at 3? So that's going to be 80 plus 30 times 3 minus 5 times 3 squared. And then you want to enter that into your calculator. And then we've got 80 plus 30 times 3 minus 5 times 3 squared gives you 125. We also need S at 1, so that's going to be 80 plus 30 times 1 minus 5 times 1 squared, which is going to be 105 meters. So now that we know those, or we calculated them, we can go back to our formula. So S at 3 is 125, S at 1 is 105, and then 3 minus 1 is 2. So we end up getting 125 minus 105, 20 over 2, or 10. But this is a average velocity or a rate of change. So rate of changes, whether they're average or instantaneous, always need units. So you have to include units here. So I usually look, okay, what's in the numerator? This is position, so that was measured, and then you check the question again in meters up here. Okay, so this is measured in meters. And then time is measured in seconds. So your units are going to be meters per second. So you can just add a little there for V average is 10 meters per second over the interval 1 second to 3 seconds. Now they want the average velocity of the pebble between 1 second and 1.5 seconds. So we've changed our interval. We already know S at 1 from what we did above. So I'm just going to rewrite that down. We already know S at 1 was 105 meters. So then we're just going to find S at 1.5 here, substituting into the formula for S at t again. And then if we enter that into our calculator, we're going to get 113.75 meters. Okay? So we're going to do the V average formula again because we're still finding average velocity. But this time it's going to be S at 1.5 minus S at 1 over 1.5 minus 1. So then S at 1.5 we figured out was 113.75 minus S at 1, which was 105. And then 1.5 minus 1 is 0.5. So that's 8.75 over 0.5. Which gives you 17. So now V average over that time interval is 17.5. And then again, you need units, meters per second. Okay. Therefore, now we're on to calculating the instantaneous velocity at 1 second. Okay, so we said instantaneous is different. This instantaneous velocity is the slope of the tangent, not a slope of a secant. So it involves calculus. So our formula for V instantaneous is going to involve the limit as h approaches 0. Now instead of an f here, we're going to use an s because there was an s in the question. So it's going to be s at, so it's at 1 second, so s at 1 plus h minus s at 1 over h. Okay, so that's instantaneous velocity involves calculus as opposed to average velocity is just slope. All right, so we already know what S at 1 is from our previous problem. It was 105 meters. But S at 1 plus h, we're going to have to do some work here. So move my paper over a bit here. 80, so plus 30 times 1 plus h minus 5 times 1 plus h squared. So that's going to be 80 plus 30 plus 30h minus 5 times 1 plus 2h plus h squared. So 80, oh, I can actually do that. Collect my like terms here. 110 plus 30h minus 5 minus 10h minus 5h squared. So 105 plus 20h minus 5h squared. All right, so now we can substitute into our formula. So V instantaneous is a limit as h approaches 0. So S at 1 plus h is 105 plus 20h minus 5h squared. And then we're subtracting S at 1, which was 105, over h. So just some correspondence again. This and this are the same, and this and this are equivalent. All right, so then if we simplify the numerator, the 105s add up to 0, and we're left with 20h minus 5h squared over h. And then we can factor h out. So the limit as h approaches 0 of h times 20 minus 5h over h. And then our problematic h cancels. So now we can take the limit. So we can let h approach 0, and our instantaneous velocity then would be 20 meters per second, therefore. Okay? So first two questions were average velocity, and we just needed to find slope really, and then, or the grade 9 slope calculation, y2 minus y1 over x2 minus x1. And then instantaneous velocity, you're going to use your limit formula from yesterday. Okay, next question. When is the pebble at rest? So this is, for this unit, our Part D question. So make sure that maybe after we go through this the first time, you guys can rewind the video and go through it again so you really understand. So it says, when is the pebble at rest? So if we imagine that a pebble is dropped from a cliff 80 meters high, so we've got our, do a little diagram here. So here's our cliff, and the pebble is dropped off, and it's going to come down and land. So there's where my pebble drops. So my pebble drops when it's positioned above the ground, so its S at t is equal to 0. Sorry, that's not, actually wants to know when it's at rest. My bad, sorry guys. So it's at rest when its velocity, so its instantaneous velocity is equal to 0. That's when it's at rest, okay? So not going to be down here because it's going to hit the ground with quite a big velocity. So it's probably going to be up at the peak up here where it's stops going up and then starts going down. So just for a split second, its instantaneous velocity is going to be 0. So we're going to start off just by getting our formula for instantaneous velocity. So we know that's going to be the limit as h approaches 0 of s at some unknown time we don't know. So we'll call that time t, s at t plus h, minus s at t, that unknown time again, divided by h. Okay, so we do know that v instantaneous then is going to be 0 at a certain time, and that's the time that we want to solve for. So in order to solve for time here, we need to find s at t plus h. So we'll do that off to the side here. So s at t plus h is going to be 80 plus 30 times t plus h minus 5 times t plus h squared, which is going to be 80 plus 30t plus 30h minus 5 times t squared plus 2th plus h squared. So 80 plus 30t plus 30h minus 5t squared minus 10th minus 5h squared. And that's a lot of terms, and none of them are like terms if you look at their endings. And then s at t was given in our question as 80 plus 30t minus 5t squared. So we've got to fit this all in here. So s at t plus h was 80 plus 30t plus 30h minus 5t squared minus 10th minus 5h squared. And then I'm subtracting 80 plus 30t minus 5t squared. And then that's all over h. So again, correspondence-wise, here's s at t plus h, here's s at t plus h, here's s at t, and here's s at t. I'll just kind of underline it because it's got this minus in front of it that you're going to distribute here. So I'm just going to move over to the side a bit so I have a bit more room. So 0 is equal to the limit as h approaches 0 of, so that's 80 plus 30t plus 30h minus 5t squared minus 10th minus 5h squared minus 80 minus 30t plus 5t squared all over h. And now we should have some zero pairs, hopefully. So we've got 80 minus 80, 30t minus 30t, negative 5t squared plus 5t squared. And then what we're left with then is 30h minus 10th minus 5h squared over h. So all of those terms in the numerator have an h in common, so we can factor h out. So that we can divide out that problematic h. So we're getting 0 equals the limit as h approaches 0 of 30 minus 10t minus 5h. Now we can let h approach 0 because the denominator does not approach 0. And we'll get 30 minus 10t, add 10t to both sides. Divide both sides by 10, and we get t is equal to 3, and then our units were seconds. So that means, therefore, the pebble is at rest at t equals 3 seconds. Okay, so recap for this question. What you had to realize to be able to do it was that v instantaneous is equal to 0 when the pebble is at rest. So those two things equate to each other. So if you're asked when the pebble is at rest, it's when its instantaneous velocity is at 0. So then you just set up your formula for instantaneous velocity, replace instantaneous velocity with 0, do the work to find s at t plus h, which involves some algebra. Follow through your limit all the way to the end. And once you let h approach 0, you should be left with a term containing t so that you can solve for the time when the pebble is at rest. So that's our part D question for this unit. On to the next question. So This question says the position of a particle is given by the equation s at t equals the square root of 4t minus 3, where t is measured in seconds and s is measured in meters. Find the average velocity. Okay. So this is the slope of the secant type of question from t equals 1.75 seconds to t equals 3 seconds. So velocity they're using again, so we could say v average is going to be s at 3 minus s at 1.75 over 3 minus 1.75. And then notice this correspondence here. So if you have 3 here, you have to have 3 there. 1.75. You have to have 1.75 here. Okay, so then we just have to find those numbers. So s at 3 is the square root of 4 times 3 minus 3, or the square root of 9, which is 3. And s at 1.75 which is the square root of 4, which is 2. So then we can substitute them in. So V average is equal to 3 minus 2 over 1.25. So V average is 1 over 1.25, which turns out to be 0.8 meters per second. Remember, you have to have units with your answer, 0.8. And then the numerator was change in position, and that was measured in meters according to the question, and change in time measured in seconds. So that makes the units here in meters per second. So find the average velocity, just put a therefore in front there. Average velocity is 0.8 meters per second. All right, instantaneous velocity. Find the instantaneous velocity at t equals 3 seconds. So that's a different formula. V instantaneous is equal to the limit as h approaches 0 of, again, they used s, so will we, s at 3 plus h minus s at 3 over h. So we already know s at 3 from the previous question was 3. S at 3 plus h is going to be the square root of 4 times 3 plus h minus 3. Which is the square root of 12 plus 4h minus 3, which is the square root of 9 plus 4h. So we'll go back here to our formula now. We can substitute in limit as h approaches 0 of the square root of 9 plus 4h minus 3 over h. So now we're going to multiply top and bottom by the conjugate of the numerator. So if we do FOIL then in the numerator, we're going to get, so the first times the first just undoes the square root. And then plus 3 root 9 plus 4h. Minus 3 root 9 plus 4h minus 9 over h times the root of 9 plus 4h plus 3. So the limit as h approaches 0. So those add up to 0. So we get, and the 9 minus 9 add up to 0. So we have 4h over h times root of 9 plus 4h plus 3. H's divide out. So now finally it's safe to let h approach 0. So we can take the limit. So we're going to get 4 in the numerator and the square root of 9 plus 3 in the denominator. So 4 over 6, which is 2/3, and then meters per second. So the instantaneous velocity, so therefore v instantaneous is 2/3 meters per second. So that means at 3 seconds, the velocity right at that instant is 2/3 meters per second. Next question. Last question. So question 3. A doctor administers 10 milligrams of a radioactive tracer dye into a patient before a heart scan. The amount of dye in the body, T hours. Okay, so those are our units of time is hours. And our units of amount is milligrams. After being injected is given by the function a at t equals negative 0.2 t squared plus 10. So how much dye is in the body after 2 hours? So notice how this question doesn't ask for any kind of rate, average or instantaneous. No rate. It just asks how much dye is in the body after 2 hours. So really they're just asking you a at 2. So you just replace t with 2. And determine that on your calculator, and you'll get 9.2 milligrams. Okay, so it doesn't ask you for a rate. Make sure you don't assume what the question is. Next question asks what's the average rate over the first 2 hours. So that's something too that we haven't kind of talked about yet. Average rate we have, but what happens when it says over the first 2 hours? So that means you have to be able to know that that means from 0 hours to 2 hours. So you assume you're starting from 0 if it says over the first 2 hours. So we can use, since we're not talking about a velocity, we could use m average if we want to for average rate. And so that's going to be a at 2 minus a at 0 over 2 minus 0. So a at 2 we figured out in part A of the question was 9.2. A at 0, you can figure that out by subbing it in. It's just 10 over 2. And then we can do that on our calculator. So 9.2 minus 10 is negative 0.8 divided by 2. Is negative 0.4, and the units for the amount was milligrams. The units for the time was hours, so it's negative 0.4 milligrams per hour. So if a doctor administers the tracer dye, then it starts to leave the body, so that's why the rate of change, the average rate of change over the first 2 hours is negative. Okay. And then part C, what is the instantaneous rate of change of the dye in the body at t equals 2 hours? So that's going to be our m if we want instantaneous. So now we introduce the limit as h approaches 0 of a at 2 plus h minus a at 2 over h. So then we're going to have to figure out what a at 2 plus h is. So a at 2 plus h is going to be negative 0.2 times 2 plus h squared plus 10. Negative 0.2 times 4 plus 4h plus h squared plus 10, which is going to be negative 0.8 minus 0.8h minus 0.2h squared plus 10, which is going to be 9.2 minus 0.8h minus 0.2h squared. Okay, so we're ready to substitute in now. So it's going to be the limit as h approaches 0 of a at 2 plus h, which was 9.2 minus 0.8 h minus 0.2 h squared. Then subtract a at 2, which was 9.2 over h. 0 pair on top here. We can factor out the h in the numerator now. And then divide out our h's. So our problematic h divides out. So we're just left with the limit as h approaches 0 of negative 0.8 minus 0.2 h. Safe to let h approach 0, and we end up with negative 0.8 units again, milligrams per hour. So therefore, the instantaneous rate of change of the dye in the body at 2 hours is negative 0.8 milligrams per hour. And that was the last question. So success criteria, you can find the average rate of change of a function over an interval of time, t equals a to t equals b, by applying the formula average rate is s at b minus s at a over b minus a. You can find the instantaneous rate of change of a function at an instant in time, t equals a, by applying the formula instantaneous rate is the limit as h approaches 0 of s at a plus h minus s at a over h. And we know that rates of change require units of something that changes with time. So examples would be meters per second, milligrams per hour, people per year, etc. Okay.